Interference from thin films. Many colors in our daily lives, such as colors on a soap bubble, an oil slick when sunshine falls on them, are caused by interference of light waves reflected from the front and back surfaces of a thin, transparent film. The film thickness is typically of the order of the magnitude of the wavelengths of the light involved.
Soap bubbles display dazzling colors when seen under bright light. If we dip this cylinder into a soap solution, a thin flat film is placed on the mouth of the cylinder. We'll shine the light off the soap film and onto the screen to show how the colors we see depend on the thickness of the film. Immediately after the film is produced, the colors are pale and difficult to see. As the fluid drains to the bottom, the film thins at the top and the colors become more distinct. Now the film is so thin at the top that the colors have disappeared, leaving a dark space where almost no light reflects. Finally, the film breaks.
Now, we look at this is the light shining almost perpendicular to the film. This is the film. So perpendicular means theta is approximately to 0. And second, the wavelength of the light is at the same magnitude of the thickness of the film. The air is approximately in the magnitude of the wavelength. Now, we are looking at this film in front of this film here. Two lines get into our eyes. One is reflect direct from this one, the black one. The other one is at this border, it refracted and hit this point B. At this B, it has two branches. One is refract to in3, one is reflect back in this medium. And the point of C, we have two branch. One is reflected and one is refracted R2. And what we see is R1 and R2 in our eye. They would interfere with each other. Region AC is AC. On the film of the observer will be maximum is bright if the ray 1 and ray 2 are fully in phase. Or it can be minimal, as dark, if ray 1 and ray 2 are fully out of a phase. Or there is intermediate interference in the brightness between them. Compared to Young's experiment, these two lines get into eye. They have 2 points in difference. One is before recombine, two rings both undergo reflections on surface. This one reflects on the front surface, and this one reflects on the back surface. One of the rays, ray 2, travel in another medium with different index of refraction. This index M2, this index N1 are different. Will these facts affect the calculation of the phases different between them? The answer is yes. Now let's see how. 3 ways in which the phase difference between two waves can change. In the same medium, by the waves traveling along paths of different lengths, their phase change. Second, by reflection. We will talk later. 3, by the wavelengths traveling through mediums of different indexes of the reflection. Even they have the same length, but they're different media with different index of refraction, so they have different effect. Let's first study reflection phase shift. The phase difference between two waves can change if one or both are reflected. We have learned in mechanics way, we know that's one. If the two lobe, this is an interface. If the waves from hard rope to the soft rope, it comes back with the same phase. If the wave from the soft rope to the hard rope, and they come back with a change of phase, 1 pi, phase pi or half length. Okay? The same thing happens in the light wave. If the light incident at the interface between medium with different indexes of refraction is in the medium with a smaller index of the refraction, the reflection causes a phase change of pi radius or half a wavelength in the reflected wave. Otherwise, there's no phase change due to the reflection. So that means when you're reflection, you can have a phase change or not have a phase change. That depends. We say higher means half. What I mean high means if you go to the higher index of refraction and reflect it, and you have half wavelength phase change. We can summarize these results from light in terms of the index of refraction of the medium of which or from which the light reflects. From above we know N2 is larger than N1 and N1. We look at this line. This line is a high index of refraction to the lower index of refraction. So it is of lower index of reflection. So this reflection does not have phase change. Look at this line. This line is from medium low index of refraction to higher index of refraction. So it is of higher reflection, then you have 0.5 half wavelength phase shift. This might be remembered as higher means half. You go to higher, you had a half wavelength change. You get to lower, fine, no phase change at all. Okay? No reflection ray under phase shift. All these reflects now from here to here, from here to here, from here to here. Okay, reflect. No phase change at all. Only reflected phase. In accounting of phase difference in terms of length difference, we notice that one of the rays in the interference from thin film is traveling in a different medium from the others. Because the path length difference to air is measured within the film. It's a number of wavelengths travel in this medium that is important in finding the phase difference of the wavelengths at I. We know that the wavelengths change in different medium with different index of diffraction, N. It will shorten. This is the wavelength in the vacuum. This is the index of refraction in this medium. Okay? So the same length, the number of wavelengths is counting different. You divide by the lambda n. And the lambda n, we know that this lambda, you put this one inside. Look at this, 2n, okay. We can look at this in another way. This one, the length in a medium with index of refraction n can be equivalent to n air length in vacuum. And this is wavelength of the vacuum. Okay, it's very clear. You can treat the film with thickness of NL in vacuum. So you divide by the wavelength of the vacuum. Either way, you can do it. Now we go back to our topics. Film interference. This is the film with index of refraction N2. This is N1, this is N3. Suppose this is the glasses or the water, and this is air. Now, what the situation here is, N2 is either larger than N1 and N3, or N2 is smaller than N1 or N3. In this case, then we will see that two lines, one of them has reflection phase change, half lambda. Okay? So the maximum is this 2. That's equivalent to N to L in vacuum. Okay? And one of them, you have phase change, half lambda, either here or here. Okay? Depends the situation. Okay? If this is larger than the one, then we see this one, you have higher means half. If this is smaller than these two, and here you have higher and half. So anyway, you have beside the distance 2 and L, you have half lambda phase change. If totally the difference is the magnitude, the integral number of wavelength, this is a maxima. Okay? You get it? The maximum is 2 and L. Plus one of them have half lambda. The situation is N2 either larger than N1 and 3 or smaller than N1 and 3. In this case, one of them has phase change. We rewrite this form, move this here, so we get this M can be 0, 1, T. Rewrite this one, we get 2 and L equal to M minus F lambda. This is the condition, okay? The minimum, we see 2 and 2 plus N equal to M lambda plus half lambda or minus half lambda, okay? This is the minimum condition. And we rewrite this one, we cancel the M, we find 2 ms equal to M lambda is the condition for minimum. Okay. This equation holds when the index of refraction of the film is either greater or less than the indexes of the median on each side of the film, on each side. If not the situation, then this formula is not true. Okay? So this formula is deduced under the condition N2 either larger than N1, N3 or smaller than N1, N2. If the film thickness is not uniform, lines of a maximum and the minimum intensity will appear fringes of the constant thickness. If the thickness is the same, you have the same fringes.
When two transparent plates are pressed together and viewed in a bright light, interference patterns can often be seen. We'll use this monochromatic sodium light and two large glass plates to demonstrate one type of pattern. With just one glass plate in place, the reflection of the sodium light is uniform. When we add the second plate, an interference pattern appears. The pattern shifts as the flexible pieces of glass relax into position. Squeezing down on the plates causes a shift in the pattern. We'll use these glass plates with a thin coating of transparent magnesium fluoride to demonstrate interference of light reflecting from very thin films. The thickness of the coating determines which colors are reflected and which are transmitted. This first plate has a relatively thin coating of magnesium fluoride. It reflects yellow light and transmits blue light. This plate has a slightly thicker coating. It reflects violet light and transmits green light. This plate has a still thicker coating. It reflects green light and transmits red light.
Here are two glass plates, with one resting on top of the other in a circular frame. The lower surface of the upper plate is slightly convex, as shown in this drawing. When we reflect light off the glass plates and onto a screen, a circular interference pattern appears. When we press down on the upper plate, we decrease the minute separation between the plates, and the pattern shifts as a result. Here is the light from a mercury lamp shining straight onto a screen. If we reflect the light off a sheet of mica and onto the screen, an interference pattern appears. The light is reflected from many thin layers in the mica, creating a circular interference pattern of violet and green rings.
Sample. White light with a uniform intensity across the visible wavelength range, 400 to 690 nanometer, is perpendicularly incident on a water film. This film is water, of index of refraction N2 1.33 and a thickness L 320 nanometer. That is suspended in air. At what wavelength lambda is the light reflected by the film brightest to an observer? We know that's when the index of refraction of the film is larger than both sides, so we can use the formula we deduced above. So the maximum is 2 half over n plus half lambda. In other words, 2nl is equal to m plus half lambda. That's the maximum. Okay, and then we see n is 1.33, l is 302. With this is nanometer as a unit. Okay, so let's put the number inside, and we put the m. We look at m can be 0, and we put the lambda is 173. N equal to 1 maximum, and we get lambda 6 with 8. M equal to 2, we get lambda maximum 4. And from this range, only this is qualified. So lambda equal to 5, 6, 7 nanometer light is qualified. Sample. In figure, a glass lens is coated one side with thin film and magnesium fluoride to reduce reflection from the lens surface. That means this reduced reflection. This is 0, maximum. This condition is maximum. Minimum, sorry. It's minimum. You cannot see that. This is reduced. The index of refraction of magnesium fluoride is 1.38. This is the one. The glass index of refraction 1.50. The air index of refraction is 1.0. Okay. Now, this situation is not satisfy the one we deduced above. Okay, because this is smaller than this one, larger than this one. We have to analyze it in detail by ourselves. What is the least coating thickness that eliminating via interference the reflection at the middle of the visible spectrum? For this one, this is the minimum. Okay, so you go inside. Assume the light is approximately perpendicular to the lens surface. Now let's analyze in detail. What is the phase difference? Okay, or both reflection causes the same phase shift. Now, this light reflects from low to high. High means half. And this light reflect at this border is higher than in half. Okay, so both line undergoes phase change. That's equivalent to nothing happened. No phase change at all. Okay, so the minimum is this length. This length is 2 N2L. This is equivalent to the vacuum length. Okay, the minimum is m plus half lambda. Okay, this is in vacuum. Okay, so we get this one. If m equal to 0, m is 0, you get a minimum. This is 0, you get L equal to lambda over 4nt. Okay, put it on the side. We get a nanometer. Okay. Sample. Figure shows a transparent plastic block with a thin wedge of air. At the right, this is air. The wedge thickness is exaggerated in the figure. This is exaggerated, very thin. This is a wedge, so this is the separation air on the right side. This is separation air on the left side. They're different. A broad beam of red line with wavelength lambda 632.8 nanometer is direct downward, so the top of the block at the incident angle of 0. Okay. Some of the light is reflected back from the top and the bottom surface of the wedge. This is the one. This is the wedge from top and wedge, which acts as the thin film. So in this case, the thin film is air. Is air. It's very thin. Okay, and the thickness varies uniformly, and gradually from air to air up. Okay. The plastic layer above and below the wedge of the air are too thick to act as a thin film. Remember, only thin film can interference. Thick one cannot. You cannot see the one. Okay? So in this case, this plastic does not play the interference here. Only the air, thin film. Okay? An observer looking down on the blocks is looking down. See, our interference pattern consists of 6 dark fringes and 5 bright red fringes along the wedge. What is the change of thickness delta L along the wedge? Now we see 1, 2, 3, 4, 5, 6 dark. 1, 2, 3, 4, 5, 5 red fringe maximum. Okay? Now, if you look at this one, our eyes are on top, look down, we see this one. And we look at the reflection. What we see is 2 lines. One line reflects from the top fringe, one line reflects from the bottom fringe. And we see that one, okay? This one, N1 equal to N3, okay, both sides, N1, N3, this N2, okay? N2 is smaller than both sides. So we satisfy that only one have phase change. Okay, if we look at this R2, low to high, high means half. And this one is not high, so we don't have a phase change. So we have only one have phase change. And what we see, the dark is fully destructive. Okay, that means the total length 2N2L equal to maximum. This is the minimum condition. Okay, the formula we deduce above. Okay, now at the left, on the left, we have the right, we have minimum. What the difference? Now, it's 1, 2, 3, 4, 5. So if this is the M this must be m plus 5 because it tell you the 6. Okay, with these two formula, I can find the delta L. Okay, it's a very simple equation. Find lambda over 2 and 2. We put a number inside, we get the answer. Okay, this is the wavelength we know. This M2, okay, we know is air. Okay, so we get an answer. 1.58 times 10 to the minus 6 is micrometer. Okay. Sample. A glass plate of index n1.60 is touched with another glass plate of index 1.80 at one end and form a wedge of angle 0.50 as shown in the figure. This is air. A broad beam of light wavelength 500 nanometer is normally incident down so the top. Okay? Question A. What is the separation between the two adjacent fringes? By the observing, looking down so the top plate. You look down here, you see what the difference, separation between the fringe. Question B. What is the separation between the two adjacent fringe? If the wedge is placed in an oil of index N0 1.70, instead of 1.00, we put the oil with index of reflection 1.70. So what is happening? Okay, now this one we see that one. If this is air, so this is satisfy our condition. The N2 is so this is the thin film, not these glasses. These glasses too thick to interference. Okay, so in our case, this is a wedge, air is a thin film. Okay, and this is the index of fraction, the 1.00 for air. And we look from depth so to the line. Okay, this is the top face. This is the bottom face. Okay, we see the top face when you reflect. This is not higher. So, and then you to the second one you reflect is higher. Higher means half. So when you look up from bottom, from upside, two line, one of them has phase change. So the delta L equal to two different 2 N O Z D. This is D is the thickness. You have one of them have a phase change. This condition satisfied. Now so look at this one. At contact points, D equal to 0. D equal to 0, delta L equal to half lambda. That means this is minimal. What we see in this case is dark. It's dark. Okay? Dark green. Then when the second dark, because what we wanted the separation between these two. The second dot means half lambda plus lambda is 3 over 2 lambda. And from here, we get this one. There's 3 lambda over 2, we find the D. The D equal to lambda over 2 and 0. Okay, then we have this D. This is the D. So we know D. What we ask is this one. This one, okay? So we find out this is this one. Whether we find that D is this one. So we have to transfer this one. This one is very easy. This one equal to D divided by tangent 50 in this rectangular. Okay? So we put this number inside, we get the number. Okay. Delta L is the separation of two fringes. If you look from the up, okay, up down. Yeah. We have to separate this delta L, this one, and this delta small L, and this one. And we are asked to find the delta small L. Now, if we put this one in the oil with index refraction, diffraction 1.70, the situation will be different. You know what the difference? You reflect from this one is higher. 1.60 to 1.7 is higher means half. And then on the second, the back floor is 1.7 to 1, also high. So both reflect rays undergoes phase change. That equivalents nothing. Okay, and we look at this contact point. Okay, point of d equal to 0. We put the delta L difference, delta L equal to 0. So this, in this case, if put oil, this H, we see the bright fringe. Okay, and the second bright phase, this delta L equal to lambda. And delta L to the lambda, I put this one. Okay, we get the lambda, so the d equal to lambda over 2m0. All right, you get a d. And we want to find this one. So delta small l equal to d over tangent 0.5 degree. Okay, and we get a delta L. Put everything inside. We get, it's different. Okay. Sample. Coating a transparent film of index N2 2.50 on the glass plane of index N1 1.50 can reinforce light reflection. The intensity of the transmitted light, measured from the back of the glass plane, will change along with the thickness of the film, while a monochromatic light of wavelength lambda 600 nanometer is normally incident from the top. What is the thickness of the film when the third minimum intensity of the transmitted light happens? This question means we look at this line, transmitted line, from here, okay, not from top, from bottom. We look at the line, this line transmit direct to this one. You know, transmitted line never has phase change. And the second one will be the black one. It reflects from this one, go back. And the transmitted, it also reflects from this source and goes through. So these two lines are the one that interferes with each other. And let's see what their phase different or length different. We know this line, no phase change by reflection at all. So the only difference is the 2D, okay, in this medium. So equivalent to delta L 2N to D in vacuum. Okay. The minimum condition is this equal to M plus half lambda. It's condition for minimum. Okay. And our condition is the third minimum. M can be 1, 2, 3. The third minimum, M equal to 2. We put it sign and we find D, thickness of D. It's a very simple one, okay? And this is 5 lambda over 4, let's say. We put on the main side, we get a D. That's minimum.